Now that we have our polyatomic ion chart in front of us, we'll begin examining compounds that contain polyatomic ions. Of course, that prefix poly meaning many atoms acting as a group carrying a charge. They are polyatomic ions, so single ions, even though they contain multiple elements and many different kinds of endings, they contain just one charge. When we identify polyatomic ions, we do so by using parentheses around that ion in the formula. And we name and charge of the polyatomic ion simply do not change. Just as a monatomic ion has a single element carrying a charge, polyatomic ions are multiple atoms grouped together by a covalent bond. They're sharing electrons, acting as a unit, but they've lost or gained electrons and thus carry a charge. We simply name any ionic compound that contain a polyatomic ion by naming the cation first and the anion last. Same set of rules, but we're inviting more players onto the field. Name the cation first, the anion last, and we name them according to charge. Here are some common polyatomic ions. This is from our text. By no means is this the exhaustive list of the polyatomic ion chart I asked you to print from our Blackboard site. The first is called acetate. ACETATE is called acetate. Its formula, C2H3O2, and that whole group of atoms carries a -1 charge. Acetate, a group of nonmetals acting as a unit carrying a charge. Carbonate, CO3, carries a -2. Carbonate, you might have heard of carbonated beverages. They give us the bubbles when we open a can of pop. Carbonate is a polyatomic ion. It is made of 1 carbon and 3 oxygens, all together as a group, and as an entire structure carries a -2 charge. Hydrogen carbonate. Sometimes you'll hear that called bicarbonate. HCO3 acting as a unit with a -1 charge. The base ion, opposite of acids, we have bases. The base ion is called hydroxide, OH -1. Nitrate, NO3, it carries a -1. One less oxygen, hear how the 8 becomes an ite? Nitrite is NO2, -1. Chromate and dichromate. CrO4 carrying a -2, Cr2O7, who also carries a -2, respectively. The one and only one positive polyatomic ion is called ammonium. NH4, it carries a +1 charge. Notice in the far right column, I see a family of ions, and this is worth discussing. Hypochlorite, chlorite, chlorate, perchlorate. Let's examine those prefixes and the suffixes, the beginnings and endings of the names as we explore the formula. The root word is the ATE ending. Chlorate has ClO3, a group of atoms acting as a unit, and it happens to carry a -1 charge. When we remove 1 oxygen and go from a chlorate, ClO3 negative, to an ite ending, ClO2 negative, when 8 becomes ite, we've removed 1 oxygen. If we remove yet another, we form hypo. Hypo is a prefix that means below. Below the normal level is hypo. Hypochlorite, ClO1, negative charge of 1. Again, the root word chlorate, remove 1 oxygen. Chlorite, remove 2 oxygen. Hypochlorite. The root word chlorate, if you add an oxygen, perchlorate. Hyper. Hyper means above. Hyper, above, hypo, below. But instead of calling it hyperchlorate, they simply have shortened the name to perchlorate, ClO4 with a -1 charge. And notice this trend, sulfate, sulfite. The ate ending has one more oxygen than the ite ending. Hydrogen sulfate has an H. H is a positive one, so if I add it to sulfate, SO4 -2, it becomes +1 with a -2. +1 with a -2 is a net -1. Sometimes we hear the word bi, Bi, that little prefix represented that hydrogen. You have bicarbonate, called hydrogen carbonate. You have bisulfate, called hydrogen sulfate. And hydrogen sulfite, sometimes called bisulfite. This is a simplistic list of the polyatomic ions. There are many, many more, and I've given you that pattern or a polyatomic ion chart to refer to some more and more common names as we begin to hear them. The patterns for polyatomic ions. The elements in the same column tend to form similar polyatomic ions. And so, for example, the number of oxygens, notice those polyatomic ions on that previous slide. What makes a polyatomic ion is a number of oxygens that attach themselves to some other nonmetal. Chlorine is in the same family as bromine. When they form a polyatomic ion, you get chlorate or bromate or iodate. They're all in the same family. If the polyatomic ion has a hydrogen as part of its structure, you'll hear that as hydrogen carbonate or hydrogen bromate, but oftentimes you'll hear it abbreviated. It's kind of like the common name called bicarbonate instead of hydrogen carbonate. It's just a shorthand way for saying hydrogen. Look at the patterns on our polyatomic ions with the ATE. I call that the root word. Borate from the element boron. Carbonate from the element carbon. Silicate from the element silicon. Nitrate is from nitrogen. Phosphate, arsenate, the elements of phosphorus and arsenic. Sulfate, selenate, tellurate. The elements are sulfur, selenium, and tellurium. Chlorine becomes chlorate. We have bromine becoming bromate. Iodine becoming iodate. There's a definite periodic trend according to the families they live in with how many oxygens attach and the charge that they carry. You do not need to memorize these. You will always have access to a polyatomic ion chart. The one, hopefully, that you've printed, a very thorough polyatomic ion chart, the one that you've printed from the Blackboard site. So as I look for patterns for polyatomic ions, the ATE ending tends to be what we call the root word. And if we add or subtract the number of oxygens, we change either the prefix or the suffix. If the root word is chlorate, ClO3 negative, and we add one oxygen to become ClO4 negative, hyper, per, meaning above the normal, we get perchlorate. ClO4 negative is called perchlorate. What if we subtract an oxygen? The ate ending changes to an ite ending. Chlorate, ClO3 negative. Chlorite, ClO2 negative, removing an oxygen to one below the normal. And if you remove yet another oxygen, we get the prefix hypo with the suffix ite. Hypochlorite, ClO carrying a -1. This is what I'd call a family of ions, all with the root word of chlorine. Here's an example where we're being asked to name the following ionic compound. Now keep in mind, I don't care how many letters there are in the formula, there's still just one positive and one negative ion. Ionic compounds are built of a single cation and a single anion. So as soon as I see this formula, Na2S2O4, I know that we must have a polyatomic ion because there's three different symbols, Na, S, and an O. That's three symbols, and yet I'm only allowed two names. Start by naming the positive ion first, just as any of the rules asked us. The positive ion Na is found in group 1A. Its name is sodium. Because it lives in group 1A, we know it to be a +1 charge. Leaving a group of atoms acting as a unit carrying a negative charge, the very definition of a polyatomic ion. Find your polyatomic ion chart that I asked you to print. In the middle column, halfway down or so, you will find a polyatomic ion, SO4, with a -2 charge. Its name is sulfate. Name the positive, sodium. Sodium, it lives in group 1A. We know its charge. It's one of those metals that has an invariant charge. It does not change depending on what it hooks to. Na is always the sodium ion. SO4 is the polyatomic ion called sulfate. SO4 carried a -2 charge. When we put together the names of the ions, we come up with sodium sulfate. Sodium sulfate is the name of the compound with Na2SO4 as its formula. Notice we did not include a Roman numeral in the name. Sodium does not require one. Excuse me. Let's try naming an ionic compound. It has a polyatomic ion, and yet I notice the first name, Fe, which stands for iron, lives right in the heartland of, I don't know your charge by where you live. I don't know your charge. It's variant. The small columns in the middle, those transition metals, require a Roman numeral. They have the ability to change charge based on where they live. Fe stands for iron. NO3, notice it's in a parenthesis. The parenthesis is grouping together a polyatomic ion. Its formula is NO3. The parenthesis is outside the NO3. It's said to read as taken 3 times. Now let's put that together. Fe, NO3, taken 3 times. That group inside the parentheses is NO3. It's a polyatomic ion. Look up its name. No need to memorize. Find its name on the polyatomic ion chart. It's called nitrate. Now, iron requires a Roman numeral. Notice the charge on the nitrate. On your polyatomic, its first column, halfway down or so, you find NO3 carrying a -1. The -1 charge tells us that nitrate carries a -1, but see the outside the parenthesis is 3 units of that -1. 3 units of a -1 gives us a net charge of a -3. Therefore, iron must be carrying a +3 charge. Simply thinking about uncrisscrossing the subscripts to find the charge helps us see that pattern. Name the cation. Iron, Roman numeral 3. Name the anion. NO3 -1. It's called nitrate. Put it together, we simply find the name of our compound as iron, Roman numeral 3, nitrate. Fe, NO3, taken 3 times, iron 3 nitrate. Try this with your polyatomic and periodic table. What might be the names of the following compounds? Remember the rules. Name the positive ion. Check to see if it needs a Roman numeral. Name the negative ion. Positive ions might need a Roman numeral. Negative ions will either end in "ide" if they're monoatomic, or they'll end in "ate" or "ite" if they're polyatomics. Spend a quality moment with your polyatomic ion chart and your periodic table and name the following 3 compounds. Pause the video, work this through, start it up again when you're ready to check. How'd you do? NH4 is a positive, the only positive polyatomic ion we have. Its name is ammonium. The monoatomic anion, Cl with a negative one, called chloride. Monoatomic negative ions end in "ide." NH4Cl is called ammonium chloride. Number 2, Ca, C2H3O2 taken twice. Hear how I'm reading that parenthesis, taken twice. The name of the positive, calcium. Does calcium need a Roman numeral? Of course not. It's in group 2A. Calcium has an invariant charge. It does not change. C2H3O2 is a polyatomic ion. Locate it on your polyatomic ion chart. It's in the first column, just a couple down, acetate. C2H3O2 negative 1 is called acetate. Notice how we crisscrossed charges? Ca is a +2, acetate is a -1. Inside of a parenthesis, we're taking 2 groups of the acetate to neutralize the +2 calcium. Cu stands for the element copper. Copper lives right in the heartland of the transition metals. It must have a Roman numeral in its name. NO3 is a polyatomic ion called nitrate. It carries a -1 charge. NO3 is a -1. 2 groups of a -1 give me a net -2 charge. What's the charge on the copper to neutralize a -2? You guessed it, just by uncrisscrossing that subscript way to the outside of the parenthesis. That 2 is the subscript coming from copper's charge. Cu, NO3 taken twice, is copper 2 nitrate. Here's an example. Writing formulas for ionic compounds that contain polyatomic ions. What if we look at a name and want to write the formula? Step 1. Write the symbol for the positive ion with its charge. The positive ion, iron 3. Iron's symbol is Fe. It carries a +3 charge. The Roman numeral tells me the charge, not how many. Now, go to your polyatomic ion chart. Here's how I know. See that 8 ATE or ITE endings always show a polyatomic ion. "Ide" means monoatomic. "Ite" means polyatomic. Write the symbol for the negative ion. Phosphate is PO4, carrying a -3 charge. Just as we would binary compounds, ternary compounds are no different. Write the positive ion, write the negative ion, and consider charges. Iron with its +3, phosphate with its -3, already balance electrically to be 0. So if I consider crisscrossing charges, notice the subscripts, Fe3, PO4 taken 3 times, can be reduced to a simpler ratio. FePO4 is iron 3 phosphate. A +3 and a -3 already balance to a net charge of 0. We do not need any subscripts to help that out. Iron 3 phosphate, FePO4. Write the positive ion first, write the negative ion last, and consider charges. Try some on your own. What are the formulas for the following compounds? Aluminum sulfate, chromium 2 hydrogen carbonate. Please pause the video. Please give yourself this chance to practice your skills. So important to getting success in chemistry. Learning the language of chemistry is such a critical step. Pause, spend time with your periodic table and the polyatomic ion chart, and just restart when you're ready to check your work. How about the aluminum ion with a +3? Sulfate carries a -2. When we crisscross, remember polyatomics must be placed in a parenthesis to take groups of them. Al2SO4 taken 3 times. Chromium 2 hydrogen carbonate. We could also call this chromium 2 bicarbonate. Chromium, Roman numeral 2, tells us the charge. Chromium with a +2. Hydrogen carbonate's a polyatomic ion, a group of atoms acting as a unit carrying a charge. HCO3, its entire structure carries a -1 charge. Crisscross the charge of a +2 with a -1. Notice in a parenthesis, the entire polyatomic ion goes in a parenthesis. Cr, parenthesis, HCO3, all taken 2 times, creates an electrically neutral compound. When writing polyatomic ions in a parenthesis, never, ever, might I say ever, change the subscript in the polyatomic ion. Always put it in a group and place that in a parenthesis. In a new topic, we see the hydrates. Hydrates, compound, okay, completely different topic, kind of switching gears to a new category. What do you think of when you hear hydrate? If you're dehydrated, you need to hydrate, it means water. Compounds that contain water are said to be hydrated. It's not like these compounds are wet to the touch. Just inside of its crystalline structure, you got to think at a atomic level. As crystalline structures form, sometimes these little lattice cages, these structures of crystalline compounds, trap water molecules inside. And as they create these three-dimensional cages of hydrated crystals, those waters that are trapped inside are actually adding to the weight of the crystal. Hydrates are ionic compounds containing a specific number of waters for each formula unit. The water of hydration can be driven off by heating. So you can take this hydrated crystal, put it over a flame, and heat it strongly to cause the water to actually turn to steam and leave the crystalline cage. And then it becomes anhydrous. Here's a formula, COCl2. See that little dot? The little dot I know in math class needs to multiply, but here it means attached to part of its structure, adding to the weight of this compound are 6 water molecules. When we name a hydrated crystal, we name the ionic compound as we would any other rule, and then we put a little prefix in front of the water and name the water as a hydrate. COCl2, little dot, means attached to it are 6 waters. Name COCl2. Well, CO is the element cobalt. Find it on your periodic table. Do you see cobalt? It's number 27. CO is the element cobalt. It lives right in the heartland of, I don't know your charge by where you live. I must have a Roman numeral in my name. The Roman numeral is the charge that it carries, not how many you have. Find Cl on your periodic table. The element's name is chlorine, but now it's hooked in ionic compounds. Its anion name is chloride. Cl -1. Think about uncrisscrossing. 2 units of a -1 balance with 1 unit of a +2. Cobalt is carrying a +2 charge. The name of CoCl2 is cobalt-2 chloride. Now we go to name the water. The water gets a prefix. Look at the names here that goes right in order. Hemi is a half, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. If you went on, we'll see these prefixes when we start naming molecular compounds. Since there's 6 waters attached to cobalt-2 chloride, we simply name the compound cobalt-2 chloride hexahydrate. Hydrated crystals, those compounds that as they form out of aqueous solutions, trap molecules of water inside. Notice this cobalt-2 chloride hexahydrate is a bright red color when it's hydrated. Upon heating, when you create an anhydrous form without water, CoCl2 without water has a much drier, more purple color, less rich. We have a hydrated versus anhydrous color. When we're writing names of hydrated crystal or naming hydrated crystals, simply refer to the prefix to tell us how many waters are present. Magnesium sulfate heptahydrate. Take every word and turn it into a symbol. Just go slowly until you get the practice. Magnesium. Look at your periodic table. Magnesium is an element found on a periodic table. It's number 12. What is the symbol for magnesium? Do you see it? It's Mg. Sulfate. Hear the ATE ending? 8 tells me polyatomic ion. Sulfate is a polyatomic ion, so I don't have to memorize. I have to go to my my polyatomic ion chart and find it. Second column over, quarter of the way down, sulfate, SO4 -2. Notice how a +2 and a -2 are going to electrically balance with just 1 unit of each. How many waters attach with the prefix hepta? Count it out. What does hepta stand for? Mg with a +2, SO4 with a -2, and heptahydrate shows us 7 water molecules, and the dot in between means attached to, part of its structure adding to the weight of the crystal. The dot is showing a hydrated crystal. How about naming NiCl2.6 waters? Ni stands for nickel. Nickel lives right in the heartland of, I need a Roman numeral in my name. Nickel is number 28. Find it on your chart and prove it to yourself. Nickel is a shorty in the middle, group 1B. Oh, I'm sorry. 8B. I looked at copper. Nickel, number 28, Ni, must have a Roman numeral. Uncrisscross. If chloride's a -1, nickel must be a +2. What's the prefix for 6 waters? Hexa. Nickel 2 chloride hexahydrate. Naming hydrated crystals using our prefix for naming hydrated crystals. I'm going to pause here. We are now switching gears into a second category of compounds, binary molecular. Let me pause and upload this particular video. Start again when you're ready.